This talk is scientific but not academic overview of malware, anti-debugging, anti-disassembly, and anti-VM technologies, presented by Rodrigo, Gabriel, and Pedro. So guys, you can take it from here.
Good morning, everyone. I know it's difficult to be here so early, so I will try to not let you guys sleep. Well, first of all, the name is a big name because we wanted to actually describe exactly what this research is about, and it's all about like being very precise, giving you the methodology, giving you how we did it, and giving you the explanations of the results. But before we start, it's important to say that our team is a research team in Qualys, and well, we live here, okay? We are from Brazil. We live in Brazil in the middle of the forest, in the Amazon forest. To be honest, that's not really where we live. We live here in the carnival. That's where we go, like the parties and all that, right? I know all of you know that about Brazil, but the real truth is we live here. A really, really big, crowded town. That's where we live, okay? So this research is coming straight from Brazil for you guys. Today, we're gonna show you like how we did this research, what were the steps, and we give you also the explanation on the techniques. It's important to say that we're providing a huge paper on everything that we're showing here. All the details, much more things that we are not including on this particular presentation are on the paper. And I will be really happy if you guys read it because it was a lot of efforts to actually write it. The motivation behind something like that is because we know there is hundreds of thousands of new malware samples every week. This number is almost on the million every week, new samples, new malware. So there's a lot of people doing bad stuff out there, and we know that. Still, when we see people talking about automation, they are just automating single tasks of the process. Like when you look, for example, in projects like Kuka Sandbox, which is really cool projects, open source, available for people. But still, you need to get one malware, you need to put the malware on the system, you get the output, and then you need to look into the output to see whatever you're getting, right? That's really hard. We need more automation, we need more talks about that, about the process, and actually putting more scientific approach on that. Because I don't like when I see the industry talking about tens of thousands of samples, right, every week, but when they show you a research, the numbers actually also talk only about 1,000 of sample. So they say there is thousands of samples every week, but when they show you the numbers, they only tested against only 1,000 or maybe tens of thousands. It's far from being a really good amount. That was one big challenge that we had. How we can do that against like millions of samples. And we achieved that. The numbers we're showing are about 4 million samples malware analyzed. Okay. Also, we don't like the usage of words such as there is many. We like words like there is X, and this X being very precise. So it's not 4 million samples we analyze. It's 4,030,945. That's the precise number of samples that we look at. So before we continue, I will introduce you Gabriel, which is like the team leader of this research group, and he will explain you how we divided the techniques in different sections.
Good morning. As this is a scientific presentation, so it's important to make some definitions for everybody to have the same understanding of the topics covered here. So we based the work in 4 techniques, okay? The anti-debugging are techniques used to compromise debuggers or the debugging process itself, okay? Analogically, anti-disassembly techniques is considered techniques that compromise disassemblers and the disassembly process itself. Obfuscation are techniques to make the disassembly harder to be analyzed by a professional and also to make the signatures written more difficult. And anti-VM technologies that will be shown in this presentation means that techniques to detect or to compromise the presence of the virtual machines. So, Rodrigo, what are the objectives of this presentation?
So, as I said, we analyze millions of malware samples, right? And we're showing the results of everything that we see for each of the techniques that we analyze. as Gabriel pointed, we have like 4 different sections. I know in the name we don't mention the obfuscation, but obfuscation is something that avoids us to actually detect the other 3 sections. So that's why we have to detect them as well. And of course, the idea is to share stuff, to share information. So all the results are going to be available on the portal, and we're currently updating the analysis. We're currently analyzing more and more samples. We also updating the analysis algorithms that we're using. So you're gonna see that for the presentation, we documented all the techniques that are existent nowadays, but some of them we didn't have the time to implement the detection yet. So, but it's documented already on the paper, and soon they will also be detected. So that's something important. And of course, this is a malware analysis system, which is an open architecture that Gabriel will explain soon. And this architecture is open for the researchers, so anybody can actually use it. Just so you guys have an idea of the amount of numbers that we got only for this research, the amount of techniques that we're looking, I will show quickly, or not that quickly. Well, yeah, I think the projector actually screwed me, but yes. So just so you guys have an idea, these are like the graphs for each of the techniques that we detect. For each of them, we created graphs showing the prevalence of the techniques. So this graph also goes like two ways down. So we're talking about like 1, 2, 3, 4, 5, 6, 7, 8, 9 multiplied by 4 different techniques that we have all the graphs for you guys. So that's just for your knowledge, because we are not going to show all that numbers here because we don't have enough time for that. So before we get started, Gabriel will introduce you to the architecture that we use for your understanding when we mention like plugins, or we mention some words that are not very normal for some of you guys who don't understand the work itself.
So the DSXPE was the base project for the numbers shown in this presentation. So DSXPE is an scalable and flexible automated malware analysis. We deal with samples received for parts. So all the samples here, or most of them, are received from partners. And we have a portal, as Rodrigo shown, that shows the results for the general media and the researchers, and also partners.
An important point here is the intention is partners send us samples, we analyze them, we share back the results. Researchers can actually have access to all those results, but researchers don't send us samples for analysis. What researchers do is they contribute with code for analysis and for stuff like that. We're going to explain how that contribution works. But the main point here is this is open for the public. This is something that we're sharing all the information we're collecting.
So this map represents the distribution of our partners worldwide. So as you can see, we don't have partners in Australia, and neither does in Africa. But we hope after Black Hat, we do have some partners there. So we have a backend that's given the samples, process them. So each backend downloads the sample that was scheduled for the backends. So we written a paper for the IEEE Malware 2011 conference, only describing important details of a scheduled implementation. So there are many details in this paper. We analyze, as I mentioned, we take the samples that was scheduled and analyze them. We have 2 kinds of analysis, an static and a dynamic one, okay? We'll talk more on this later. And all the results are accessible from our portal, okay? And we have some characteristics of the DSXP project that will be shared here. The architecture deals with plugins to make the task of write an analysis code easier. And we do capture network traffic, and we unpack samples packets, okay? So we'll talk a little bit about plugins here, because it's a flexible point. So for us, each algorithm, each code that analyze samples are called plugins. They are very easy to add in our architecture. It's just a matter of putting the files with the code in specific directories in our system, and the dissect P does all the rest. So additionally, it's very easy to write some plugins, as I will show later in the next slide. And they are language independent. We have actually supporting some languages, but if a researcher wrote a plugin in another language, okay, just talk to us, and we can implement the architecture for certain algorithms to work in our backend, okay? Okay, so this is an example of plugins, okay? The first one was written in Python, and the second one in C. So as you can see, it's very easy to write a plugin. It's just a matter of writing a code that receives by parameter the sample to be analyzed, do whatever you want, and then print the result to the standard output, okay? And the system will deal with the parsing of outputs and returns back to the researcher the results. As I mentioned, we have actually two kinds of plugins. We have the static ones and the dynamic ones. This presentation was focused mainly on the static approach, okay? So, our static plugins are executed usually outside of the VM. Okay, we have some exceptions. For example, use the Titanium core for the unpacking purposes. So we have to run this plugin, this application, inside the virtual machine. So in this case, we are doing a static analysis, but inside the virtual machine.
Just to mention, Titan Core is a product by Reversing Labs, but and in Black Hat, they're actually releasing a version where we don't need to run anymore inside a VM, but they didn't have it in the past. They wanted to get to contribute with us, so we included the capability in the architecture to actually support plugins inside VMs. So that's an example of how much, like if researchers really want, we will have like the hard work to plug something in, okay?
So, the plugins handling the system, we have a fail-safe mechanism because this is a system for researchers. So if a researcher contributes with a plugin that does a specific analysis, for example, so if this plugin crashes or does something unexpected, our system will not crash. We will simply return back to the researcher the error that the plugin generated, together with the results and the time that was taken to the complete execution of the plugin.
And another important point, of course, for all the system, like all the capabilities that we have, we do use some open source software, right? And researchers sometimes come to us and say, hey, I have this open source software, maybe you want to test this against millions of samples, right? So a good example is PEV. It's an open source software by a Brazilian researcher. It basically analyzes like characteristics of PE files. We plugged it in. We found a lot of bugs on the code because it was hanging against specific malwares. It was originally made to actually analyze a normal PE, and we wrote a lot of patches back to him. So we contribute to the open source projects that we use as well. Okay, we are not just taking from the community. We really want to give it back. So if a researcher shares something and we have the capacity to actually give something back straight on the code of the researcher, we're gonna do it.
So the static plugins can be executed in two different situations. The first situation is before the malware gets analyzed in the dynamic approach inside the virtual machine. So you take the sample as a parameter, as I showed in the plugins, and analyze such a sample. Okay, after all the static plugins that ran before the execution finishes, the sample is actually analyzed inside the virtual machine. We ran the sample and we grab some results, such as network traffic that we cover in the next slide, and any other information, like files created and stuff. Okay, so after the malware gets finished the execution inside the virtual machine, we collected some information, for example, the network traffic. So there is a second place to execute static plugins. But in this time, another parameter received for the plugins is the pcap of the traffic generated by the malware. So the researcher can also research the traffic generated for the malwares, by the malwares. We have also the dynamic approach, as I mentioned, that is executed inside the virtual machine. Actually, we are currently support only the Windows OS, but this is a research project. We are always improving this system. We are always inserting new features. So soon you have support for more operating systems. So regarding the network traffic, as we mentioned, while the sample is running, we are recording the network traffic generated by the malware. So we record the PCAP to send the researcher for a study or to the static plugins that runs after the execution. And we also have the dissectors. What are the dissectors? Dissectors simply, basically, we take the PCAP generated by the sample, and we parse it and do a nice view, a user-friendly view of the traffic. So we are currently supporting IRC, P2P, HTTP, DNS, and other protocols, okay, for this user-friendly view. And we also have some SSL inspection with preloaded keys to decipher the traffic. So, Rodrigo, what are the methodologies used for this work?
Okay, guys. So, as you guys probably noted, this research, there is much more about the system that we use, right? In this research, we mentioned that we focusing on the static analysis and on the protection mechanism of the malware samples. So for that, we used 72 cores in different machines, of course, 100 gigs of memory, and we analyzed only 32-bit PE files. Okay, that's what we covered on this talk. For packet samples, for each version of the packer, we only consider one sample in the analysis. So when we're talking about these 4 millions, for each version of the packer, we only consider one sample, even though it might have like 700,000 samples, because as I said, we analyze it statically before unpacking, and because of that, each packer will give you the same results. So to not mess with our results, for the packer version, we only consider ons. Also, the unpacked samples, we only consider samples that are smaller than 4 megs. The reason for that was just performance, right? We wanted to have the 4 million samples analyzed, so we needed to be performatic. There are 2 exceptions, basically. One was the flame malware, just because it's the flame malware, we needed to talk about it, right? And the second one is the Brazilian malwares. One of the capabilities that we have with such a great amount of partners is to know from where the samples is coming and what the sample is targeting. In Brazil, that's a special case for us because the companies, the banks of Brazil are sending us the samples that target banks. So we know for sure this sample target Brazilian banks, and then we can make an exception. And because we are lazy Brazilians, right, all the malwares that we write are usually in higher level languages, so they are bigger than 4 megs. Lazy Brazilians. So the static analysis, as I mentioned, is the main focus of the presentation. Of course, it improves the throughput. If we have a good enough code, I'm going to explain we had some problems with performance, and we managed to deal with them. And of course, we are not running the malware, so the malware cannot do much against us. That's the only point in time that the researcher has an advantage, right? We have a malware sample, we can analyze it, and the sample is not running, so we are the only ones who can do something right now. We do have a dynamic counterpart. For this research, this dynamic counterpart is kind of important because there are some techniques that's not viable to detect statically. The results that we're presenting here in Black Hat do not include the dynamic counterpart of the research. But we're going to have it for more and more samples soon, and then we're going to release it as well. So everything is on the website, dissect.pe. So the malware protection techniques that we look at into this work, like the way that we collected the malware techniques is basically, we look into all the state-of-the-art papers, journals, blog posts, everything that people talks about malware, and we divided all the techniques of them. We also looked into malwares in the wild because there was some techniques that we didn't manage to find any reference in a paper or in a blog post, but we know some malware might be using it or probably is using it, just nobody ever documented because, I don't know, maybe it was not interesting. Of course, as I mentioned, like we covering in the paper all the techniques. We documented everything that we managed to find. And of course, there is always new stuff coming up. I will show there is new things that we added yesterday, for example. But Not everything we already have a detection for it. So of course we're showing the results for the detections that we have. It's very clear in the paper and in the presentation for which detections that we have. But in the paper itself, we explained each of the techniques that exist in the wild. More than just explaining it, one big difficulty that we found, and we were not expecting it, is a lot of the techniques are wrongly documented. And somebody wrote a wrong documentation in the beginning, and everybody else kept copying it. And nobody actually implemented the technique to be sure how it works or why it works. And that was really fun to see. Well, it was not really fun before because we needed to implement the technique to know how it works. But now it's fun because we can actually joke with other researchers because of that. But that also proves a point. A lot of people are like getting the malwares, they look into something, they just look for the reference, and the references are all wrong, but nobody is actually doing a scientific work on that. So nobody's actually validating. So it's interesting to see that there are some of the techniques don't work anymore, and still they are implemented by malwares, right? So I guess the malware writers are also lazy, not only in Brazil. Everything that we implemented, as I mentioned, all those techniques that we implemented, we created a minimalistic example of the usage of this technique, of the implementation of the technique, either in C or assembly code, and they are going to be available on the GitHub as soon as I connect to the internet, which is not going to be here, okay? Don't worry, I'm not going to connect here. Of course, for testing the plugins that we developed, we needed a test bed. The test bed actually was like 883 samples. It was only for testing the plugins, to validating the plugins, detecting what we needed. The number is just, like it kept growing when we needed like more and more detection for specifics. So that's the number we have. And we just used this test bed to detect like bugs on the plugin, to measure the performance of the plugin itself before running it against 4 million samples. I believe you guys can guess that running and rerunning against 4 million samples all the time is not something easy, right? So we used a smaller test bed. Each of the plugins that we wrote, we defined them as having 3 possibilities for an output or outcoming of the plugin. Of course, if there is no bugs. There's always bugs. One of the outcomes is, of course, the technique was detected. So the malware or the sample implements this technique. The other outcome is, of course, not detected. But we figure out there is a third one, which is there is an evidence. Because sometimes some of the techniques might be used for something that is not exactly the purpose that we defined. Okay? In the numbers that we're going to show you, we removed the evidence. So understand that the numbers we're showing is because the technique is there or is not there. It's not just we're guessing it's there or there's an evidence that the technique is implemented. It's for sure there, okay? There is a limitation when we're talking about static analyzing like a malware, right? What we did is we got all the executable sections and the section that the entry point relies on, is on, right? And those are the sections that we disassembling. That of course makes our lives easier and also give us better performance, but we miss some things, some of the code that are in other sections, even if they are referred by the entry point or by the executable sections, we are not analyzing them. That's one limitation of the research right now, but we're gonna cover it soon, okay? It was just a matter of collecting all the data that we wanted to show in time. So keep in mind that when we show the results, probably the numbers of detected will grow in time, because when we start to really look into all the other sections that we are not looking right now, all the samples that we don't detect anything, probably we will start showing something as well, okay? That's an important point on the presentation, and there we're gonna keep updating both the paper and the results with the time. It's going to be available on the website, and we're going to keep updating it as new techniques arrive or new numbers we have, okay? And other problem that we faced is, because we wanted to create an easy architecture that it's very easy to play code, we ended up plugging a lot of different plugins, and all of them were doing the disassembly of the code for analysis, right? And of course, that's really stupid, right? It's like stupid Brazilians disassembling the code like 60 different times for each of the techniques. You know, that might be a project made by Brazilians. So of course we decided that we cannot do that for 4 million samples and so many different techniques. So we wrote a disassembly framework that we use with the plugins. So the idea is like disassembly once, analyze many times. Each of the plugins will receive a callback for the instruction types. The plugin has interesting look. So the disassembly, of course, the most difficult part of that is because we have a disassembly framework, we might be a target of disassembly related attacks. So we try to not be vulnerable to that. We cannot guarantee. So that's also something that might be lowering the number of detected samples. Probably not, but that might be the case. Researchers who actually send code for us, if we have the code, of course, we can implement the code in our framework. If we don't have the code, we can just, like the plugin will just do the reversing itself as well. Okay, great. So executive summary. I don't know why, but we needed to put that. So it's always nice to show like a very, very hungry person saying, hey, executive summary, what is that in a research talk? The problem is like, because it's so many techniques, it's impossible to discuss all of them. It's impossible to show the results for each of them. I showed the graphs are huge. So what we did, we collected what is important, what is the main points that we got, and we are open for you guys if you need some specific information about something. Just let us know. We have so much data. Some of the things we didn't even looking at. We are not correlating some things. Like for example, let's say you want to know if two different specific techniques, just the specific ones, are implemented all together in how many samples. We can get that information for you. We just don't right now, right? So please give feedbacks. Use that information for something useful. So the first thing that I want to show is the prevalence of packaged samples in the world, okay? So we see that 34% of our samples are packaged. That's interesting because everybody talks so much about packing, analyzing packers and all that related to packers, while the majority of the samples are not even packaged. We did a little bit further, and we got, for each of the packers, we got the top 9 packers, right? And we split them in which packer is being used, which packer is being used. So UPX is still the packer that is more used in the world. That's cool, right? Everybody's wasting a lot of time automating analysis of Temida or other packers that are Armadillo, for example, but the prevalence of those packers are not really high. Okay, so that's also an interesting result of the research for you guys. But we decided to go a little bit further, and we look into the malwares, the case of the packers against the Brazilian itself. As I said, we have the data, we can just do the queries and get the information. And Brazilians is still using a lot of packers. Okay, so it really depends where you are, and that's another interesting thing. We didn't actually go down for which packer is more used in Brazil, but we can, right? We have the data on the database, it's just a matter of do the queries. Just for the reference, it's like a packer called Bobby Mini Soffit. It's weird packer, right? Brazilian made, I don't know. So the protection mechanism used by those packers, we went even further. And in the paper, yes, we have a paper, and I want you guys to read the paper, but because I know everybody's lazy as we are, I decided to show you the paper. So you guys understand that we really do have a paper, right? So in the paper, all this data is available, all the methodology, this is the number that I said. So all that methodology, everything, and all the techniques are here in the paper, okay? Each of them analyzed, each of them with an implementation code, how it works, how we detect it. But in the paper, okay, what is important is, for each of the packers, we get which version of the packer is using which protection mechanism. So that's a cool information to have. You can see the evolution of a specific packer version. You can see, like for example, the Bob Mini software, which is the most used in Brazil, is the 4th one in the world. You can see Aspect. You can see which kind of protection mechanism this specific packer employs. That's another cool result of the research. Cool. So after that, we needed to know, okay, so for the total of the malwares in the world, what is the percentage of a malware that implements at least one technique for protecting the malware from being analyzed. Either a disassembly technique, anti-disassembly technique, anti-debugging technique, anti-VM technique. And now you see it's 88%. And as I mentioned, this number is probably going to grow when we add more and more capabilities on the system. So it's interesting to see that if you have an AV detected around 90% of the samples, basically what we're saying is, if you want to have just a detection for 90% of the samples, basically we're reducing the problem of malicious code analysis, which is an unsolvable problem, right? It's not possible to solve with a computer the challenge of saying if a program is malicious or not. That's an unsolvable problem. But it is a solvable problem to say if a software uses a specific technique. And just doing that, and that's very fast to do, very easy to do, you can detect 90% of all the malwares out there, okay? So your AV is very slow, it's very everything, because maybe they want to detect 90% of the samples. We know they don't do this amount of detection. But yes, it's much easier to do that just detecting the protection mechanism itself. So one expectation that I have is that the malware authors will stop doing the protection. I hope they stop doing that, because then we go back to a challenge that is unsolvable, right? Which is defining if a program is malicious or not. If they protect the software, it's a pain to analyze, of course. It's going to be a challenge because you need to bypass all the techniques that they use, but it's very easy to detect as malicious, okay? Great. So we went a little bit further and we decided to look specifically for each of the techniques, what is the prevalence of the detection. So I was kind of surprised that anti-VM technology is still the one that is mostly used. So I was like, wow, anti-VM, I was not expecting that to be the most important result. So I said, okay, which anti-VM technique is the more prevalent? And look, 99% of the samples use the IN technique. IN is an instruction that VMware use for communicating between the guest and the host. So that means just not using VMware, you are already avoiding this level of detection. Before anybody asks us or mentions that Brazilians don't know how to do math, because there is 99% and 37%, that's more than 100, we know math, okay? We did engineering in school, we know math. There are samples who, of course, implement more than one technique. But as you can see, the more used techniques are the simplest ones for us to avoid. That's really nice to see. Because everybody talking about, yeah, real machines or whatever, you know, let's talk about something else. We don't really need to care much, okay? Cool. Looking to the anti-disassembly, the prevalence of the techniques is still surprising. If you look like, for example, the push hatch technique, the fake jumps technique, they are very prevalent. In the anti-disassembly, for example, setting the carry flag or clearing the carry flag for avoiding like the disassembly process to be correct, XORing followed by like a fake jump, a jump that the attacker always know will be taken, but the disassembler will need to follow both paths. Those are the techniques that are prevalent. Okay, the more complex ones, the very difficult ones to actually look at, they are not really prevalent in the samples. Okay, if you look into the anti-debugging techniques, is debugger present? Is the one that is mostly used to avoid debugging a malware. That's interesting, right? Because Microsoft implements this function. So thanks Microsoft for making our lives so more difficult, right? They give the features for the malware authors to actually avoid the process of analyzing them, right? All the other techniques are not that much prevalent. Obfuscation. We also looking into the obfuscation, and here we clearly see that the push head technique, which is a very simple technique for function calling, is still the prevalent one. And that's interesting because, again, I believe we researchers make a big mistake when we go to the conference and we just talk about the cutting edge things that are coming. We also need to show what is there, what is already being used, because there's a lot of complex techniques, but they are not in use. And they're not in use because security protection mechanism sucks, right? Like the security products, they need to keep up with that. And if we don't have a scientific approach for that, we're never going to keep up. So that's the message here. So as I showed, there is a lot of reasons. So now I will pass to Gabriel to tell you which of the techniques we implemented for each of these 4 categories, which is obfuscation and disassembly, anti-debugging, and anti-VM.
Okay, we documented 33 techniques of anti-debugging, okay? Among these 33 techniques that are documented in the paper, 31 are currently being detected in the samples. It means that we do have a plugin detecting 31 of such techniques. Okay, in the next slides, we'll pass quickly, because as Rodrigo mentioned, it's not possible to open here all the techniques, because there are lots of information, as you might see in the paper. So the green ones, we do have a plugin that we can say, okay, this technique is actually detected. The yellow ones, we only have plugins to detect an evidence. So it's not possible to guarantee, hey, this technique is present. But we can say, hey, there is an evidence that this technique is present. And the black ones are the techniques that we actually does not have a plugin to handle. So as you can see, there are many techniques, okay? And besides each one, we have the section of the paper that are explaining this technique. And as Rodrigo also mentioned, in the GitHub, we have, there will be an implementation of each of the technique for studying purposes, okay? So if some technique interests you, you can go to the paper, read the description of this technique to understand how this technique works, go to GitHub, download the code, and run by yourself. Okay, many anti-debugging techniques. Okay, but, okay. And regarding anti-disassembly, we have 9 techniques, including the variations, because there are many variations of the techniques. We grouped some techniques together in the same sections, okay? So the same thing, the colors, and we are detecting 8 of these 9 techniques. Okay, again, the technique, and besides the section of the paper explaining such a technique. And regarding obfuscation, we documented 14 techniques. Okay, but if someone finds a new technique or another technique that is not present here, so please send us a feedback. Hey, there's a technique that is very interesting that you did not cover in the paper. So it would be a pleasure for us to implement, to document this technique, and to give the results to the community. Okay, the anti-VM, we have 7 techniques. And we are currently detecting 6 of them. Okay, so now Rodrigo, we have some new techniques that we implemented detection, and what are these techniques?
So, so far, I guess you guys understand there's a lot of data in this research. We understand that, like, it's important to keep up with what the malware authors are doing. We do understand that, and we know that's an ongoing challenge. It's going to be very difficult to do that, right? So we wanted to actually give some examples. So for example, a researcher called Julian, he released a tool called S-Sexy in Hacking the Box Amsterdam in 20th of May, okay? And in June, we already had a detection mechanism for it. Basically, his technique consists of getting x86 instructions and converting it to the similar instructions that do the same using SSE. Because most of the disassemblers itself, they do not support SSE instructions, or they don't really understand SSE instructions, and most of the code that analyze stuff don't really deal very well with SSE. So that's a very cool tool that he released that receives as input a binary which uses x86 and gives us output another binary that uses SSE. So basically, he was bypassing everything we wrote, right? We detecting specific instructions in Intel, and he was converting that to equivalents in another version of the instruction set. So of course, we started detecting it, and he was very open to actually share the tool, sharing the information. We managed to run that. There is no samples using it yet. So that's really a brand new research that he just released. We already updated our system, and we already covering it. That's good. Another example was the flame malware, right? The flame malware came out, that's a malware talk. We need to talk about the name flame. Otherwise, that's not a malware talk, right? The industry is like that. So, the flame malware came out, they have like a Lua interpreter on the malware. Lua, by the way, is a language developed by Brazilians, and it's a very powerful scripting language, and the malware actually embedded the Lua interpreter in the malware to make it easier to the malware authors to actually expand the capabilities of the malware. So the industry came out, wow, that's cool, there is a Lua interpreter. I was like, okay, maybe somebody else did it. So we wrote a detection mechanism for Lua interpreters embedded in code, and we ran it against all our samples, and we can tell you for sure that's really brand new, okay? That's nice, they did something cool. Cool. Also, there is more new techniques. Yesterday, two researchers, Morgan and Bill, they released a paper about the Kingfisher spy kit. That's nice, right? They finally got access to the sample of the Kingfisher. As probably you guys know, it's being used by governments to monitor people. It's developed by a German company. And well, like nobody had samples of it to actually see what are the capabilities. So they released this paper and we said, okay, let's look into the capabilities of that and see how good we are doing, right? So the first anti-debugging or protection mechanism that this sample has is related to a piece of code that crashes all the DBG. We don't have a detection for that piece of code, okay? So we're writing one. That's cool enough, right? We're gonna see if there is other samples using it. That's a new technique, right? They use a bug on the debugger to actually crash it. So that's more difficult to analyze. Nice, now we know it. But they also include another technique called a DBG breakpoint override. Again, if you guys don't know what are the technique, just go to the paper section 3.33, okay? We also are lazy, so we put the section for you. The DBG breakpoint override is a technique that we cover. Then they use the isDebugger present, as I said, the mostly used technique, right? Microsoft, thank you. Yes, we also cover that, we also detect. Thread hiding, we also detect. Debug objects, we also detect. So that's cool. Out of 5 techniques, we detect 4 of them on this sample. This is a brand new sample, cutting edge research used by governments, sold by companies. That again shows that the problem of detecting malicious code is simpler than what we think. It's a matter of detecting code trying to protect itself. You're gonna catch a lot of new stuff out there just detecting the protection mechanisms. I do understand there is normal software that also use protection mechanisms, like Skype. Oh, Microsoft again, wow. They make our lives really difficult. But yes, Skype, for example, use protection mechanisms, but then it's just a few amount of softwares, much easier to whitelist, okay, than the whole amount of software that the corporations need to use, okay? So that's another important result from this talk. So, as I mentioned in the talk, there is a lot of research available, right? So we did a compilation of everything, all the techniques, everything's on the paper again. Wow, you see, I should work on marketing. I am marketing my paper, or paper, sorry. And like, all the code that we implemented is available on GitHub. You can download the samples of implementation for each of the techniques. There is no excuse to be lazy anymore and not understand them. The repository, as I mentioned, will be open just after the conference, as soon as I connect to the internet, maybe later on today. It's gitrub.com/rrbranco-blackhat2012 for the ones who cannot say it. Sorry, I'm not really good with slides. And updated versions of the paper, more information about our research, older paper that we wrote, vulnerabilities that we released, are all available on research.dissect.pe. You can go there now and download the latest version of this presentation and latest version of the paper, because the one that came with your Black Hat kit sucks, okay? Sorry guys, we were collecting the numbers. It's a lot of numbers, okay? So the version that you have sucks. Go ahead, download the latest version. It's already there, okay? Please, let people download it. Don't put our site down right now. Another research that is available for people is the portal itself. We are going to be on the booth, on the Qualys booth, and we're going to be showing the portal. So anybody who has interest to know more, to see other things, to see the report, or whatever we have on that portal for researchers, or talking more, come to us, talk to us, drop us an email, come to the booth and see what we have there. And all those statistics are always being updated. Well, the paper and this link that I gave for the paper are always going to be updated. So when you download, when you look into the presentation, into the paper, look into the beginning, there is the version number. And this version number will be incremented when we make some changes. So it's very easy for people to keep up. A conclusion for what we did, for the whole work that we did, is we analyzed 1 million samples, right? That's nice by itself. We analyzed 1 million samples against a lot of different techniques. That's a nightmare. We didn't sleep for a lot of time. Believe me, Brazilians are not that lazy. We missed a lot of parties, okay? But there's a lot of research to do. It's far from being over, okay? We need other researchers to help. We need people to actually try to do more on this field. We are open to that, but if you want to create your own project, we're good with that as well. Just let us know so we can contribute as well, okay? The portal is there, it's always being updated, talking to us, we give you accounts, you can look, you can contribute, you can give feedbacks. An important point, and I will let Gabriel talk about that, is thanking the people who actually did something very special for the research.
So, first of all, Ronaldo Lima, that is here.
Hey, Ronaldo, stand up.
Come here. Ronaldo Lima.
Thank you, man.
He joined our team a bit later in the research process, but he gave amazing contributions to this work. And Peter Ferry for the amazing papers and the great discussions through email with us.
By the now he works for Microsoft.
Julian Bremer for the sexy, for providing the main information we needed, and the reversing labs for the titanium core, the tool used to unpack samples, and all that wrote papers regarding anti-reverse engineering techniques that we use as a base for all the research, as you can see in the paper itself. Okay. So that's it. We want to thank you a lot, everybody.
Important point now. We are open for questionings, of course. We have time. We managed to do we have more slides than minutes on this presentation, okay? And we managed to do that. You see, Brazilians are fast. But for anybody who asks questions, we're gonna give a drink. That's Brazilian cachaça. And there is 3 very important uses for Brazilian cachaça, okay? You can use it for 3 different things. It's not drinking only, okay? The first one, you can clear the motor of your car. That's very good for cleaning. The second one, you can kill your brain cells, okay? You can do that with cachaça. The third one, I don't remember because I killed too many of mine. But most importantly, whoever gets the drink and has the courage, may I say the balls here, has the balls to come up and drink it, will also receive a nice Brazilian bag and a glass shot of Brazil, okay? So, questions? Yes?
You mentioned that your needs are good for detecting malware, but what kind of false positives are you getting if you start detecting just emails? Are these reliable? Because I can imagine that there's a lot of excess out there. And also, incorporate design reversing techniques for protection.
Yes, so the question is basically asking, against like normal executables, how those techniques actually behave, right? Do we have false positives? There are too many executables, real executables, actually implementing that. The big point is, the ones that implement it, it's not that common, okay? The huge majority of the main software do not have evasion or protection techniques. There's a few exceptions, as I mentioned, like Skype. And those ones, if you want to actually use that for an AV, you will need to whitelist, but that's a much, much smaller list, okay? So, yes. Just a minute, I will go. Sorry, guys. So basically, he asked if we did any kind of correlation between the techniques being implemented and well, I don't remember. Fuck, I told you I drank a lot of cachaça. I'm kidding. And the classes of the malwares and where the malwares are. No, we didn't. Okay. We have the data tool, so it's very easy. That's the kind of feedbacks that we need. Like, if this information is useful for you. Pass by or drop us an email, and we're gonna collect the information and send to you happily. So yeah.
So question for Flip. So currently, by my understanding, we for this kind of complex malware, we only can understand by manually analysis. So my question is, what's your thinking to get some fully system to reverse or automation to get the inside malware information? Because this malware is really huge and take lots of people effort to figure out the detail inside.
Well, I don't get if this is a question or more a comment. Sorry. Well, I believe like malware is a complex piece of software, right? Of course, there are many of the techniques that we cannot statically detect, right? That's why we have the dynamic plugins. Doing the dynamic analysis is a nightmare. There is one talk that is specifically going to talk about new methods that malwares are employing, like flashback malware, which actually gets a signature or like a license from the machine, and it's not going to run in another machine, in a different machine. And this is showing up now, right? There is a lot of things that we cannot detect. We're detecting what we can, what we cannot. We count on more researchers to actually contribute and help us. Thank you.
What was the performance of your code? How many seconds and milliseconds per file, and how much time total did it take to analyze all 4 million samples?
Okay, so yeah, that's an important question. We analyzed around 150,000 samples per day per machine. Okay, the machine is an octa-core machine with 8 gigs of RAM. So that's an important question. We missed that in the paper. It's not in the paper. I will update the paper with the information. Yeah, well, thanks for pointing out, actually. Yes. You guys giving the drinks?
Yeah.
Oh, okay. Sure. Just to be sure everybody's drinking. Not really. Well, since it's like for researchers, right, we expect people to drop us an email and ask for the access. There's not really an official avenue for that. And we wanted to make it very simple. It's basically, you drop us an email, we log in the system, create an account, boom, you go. Okay. Thank you.
Is the scope of this research limited to the detection of these techniques, or do you have forward-looking plans on mitigation and anti techniques as well?
Well, we are like a research team in Qualys, right? It's like Qualys pays us to have fun and to show what is going on in the world. We don't know about products or whatever. Of course, since we're doing research, we understand, we get a better understanding, we create a community, and we create knowledge. What the company are going to do with the knowledge, or what other companies are going to do with the knowledge, because we're opening the knowledge for everybody. We don't really know. I cannot tell you. Sorry.
You implemented 32-bit. Are you going to implement 64-bit as well?
Yes, we're going to implement 64 bits really soon, and also mobile. So we're going to start with Android. So I already have like a huge collection of Android samples. We just didn't have the time actually to put the data and collect information and look into that. It's a brand new like platform and stuff, and we still need to do some research on it. But yeah, we're gonna have it. Thank you.
Have you guys thought about looking at malware besides x86 architecture? Have you looked at like ARM or PowerPC or Thumb or anything?
That's actually interesting, right? I wish. We don't right now. I would love to, because there's a lot of malware targeting embedded device, and that's something important. I cannot say it is like a high priority right now for us, because the other question made it clear, right? X64 and of course mobile is probably going to be the next steps, but definitely we want to have a look into like PowerPC and other embedded devices as well.
Yes. Does your analysis trip over commercial obfuscation packages such as Securom and some of the Starforce packages?
I don't know. I need to go there, look if we got some sample with those, and I can tell you later. Yes.
Anything from EA?
Probably yes, right? I guess that those commercial tools are somehow leaking out there, and there will be people using them for malicious purpose. I'm not totally sure. I will need to go in the data and get it, and I can tell you later. Let's define there's something interesting for the paper as well.
Thank you.
Thank you. Cool, so no more questions. Nobody else wants to drink. So oh, there is somebody coming really fast from there. Okay, he deserves it.
Would you expose an API that we can submit samples to and get the results of you running your plugins, as opposed to submitting plugins?
We don't. We are actually not interested too much in competing with like Virus Total or whatever, but that's definitely something that researchers would like. I will think about that. That's a good question. If researchers start asking for it, definitely we're going to implement it.
All right. Thank you.
Thank you. Oh. So thank you guys. Now we all can sleep, drink, having fun. Thank you very much.